you just do polar coordinates on those. And then the third one, you just leave alone. Okay, so here the x and y have been turned into polar coordinates, and the z has been left alone. And so in rectangular coordinates, your x, y, z, and in cylindrical, it's r and theta. So the x and the y get replaced with r and theta, and then there's the z. Okay, and you still have this piece right here, because this is this RD theta. Remember, you have to add the r when you're doing polar coordinates. This is part of the unit of measurement, the unit of volume. And typically what you look for is you integrate in z first. Typically, you can do the different orders, okay? You can do a different order of integration, just depending on the situation. Integrate in z, and that's going to go from z equals u1 of r and theta and the u2 of r and theta. And then there's integrate in r, and that goes from h1 of theta to h2 of theta, and then theta goes from alpha to beta. Okay, so that's just like one way to do it. Okay, so let's take a look at the homework. Number 1, plot the point whose cylindrical coordinates are 6, pi over 3, and -4. Okay, so this is, so remember it's r first and then theta. So this is r is 6, and then theta is pi over 3. And then this last one is just z. So z equals -4. So so right here, these are the cylindrical coordinates, and we're supposed to find the rectangular coordinates. And so if when going from cylindrical to rectangular, you just use these two formulas here. So that's 6 cosine of pi over 3. And then y is 6 sine pi over 3. So let's see, pi over 3 is this angle here. What's that? 1, 2, 3. So cosine is 1/2. And then sine is √3 over 2. So that's going to be 3 and 3√3. So the answer should be x is 3, y is 3√3, and z is -4. So you just keep the same z. Okay, so let's see if that works. So 3, 3, 3, and -4. Yeah, that works. Okay, and then also we're supposed to sketch the graph. So we can sketch it from here. I can kind of show you how to sketch it from here. So if we want to plot the point, then, and let's do it from here. We can't do it from here now because we know that those coordinates. But, so you have the positive x-axis right here, and the positive y-axis going this way. And your radius is 6, but let's look at the pi over 3 first. So this pi over 3 would be the angle. So this angle, see if here we have x and y right there, but here they're like that. So the angle would be more like that right there. Okay, so that's looking at like pi over 3 angle right there, going from x to y. And then the radius is 6. That's this distance right here is 6. So that would be 6, the length of this. And then going down by -4. Okay, so that's where the point's going to be. that's what it's going to look like. And it looks like, whoa. Looks like the top left. Bottom left kind of looks the same, but those are the negative X and the Y axis. I don't know why they put those there. And I guess that this also should have just been dotted. Oh well. Okay, part B, you guys can handle that one. We'll just go on, we'll go on to the next exercise, okay? So you guys can handle part B. Okay, so the second one is to change this from rectangular to cylindrical coordinates. Okay, so for that, what you want to do, or what you can do, so what you can do is just like look at this situation here, just the two-dimensional aspect of it, and just take the first two. Just take the first two numbers. Ignore that third one because that's gonna just stay as z. So you go back 6 and up 6. Okay, and that's where you end up. Okay, so -6, 6. And so you want to find the, basically just looking for polar coordinates for this. So what's that angle right there? Anybody?
That negative.
Is it 90 plus 45?
90. Wait, what? 90. Oh, it's 90 plus 45, right? It's a 90 plus a 45.
Yeah.
Okay. We need to put it in radians, though.
Radians. So
it's going to be 3 pi over 4. Okay, because all the way is going to be pi, right? All the way, this is 180 degrees is pi. So this is going 3/4 of the way. So from the positive x-axis to the negative x-axis. So it's 3 pi over 4. Okay, and then r will be this distance here. We know this is -6. We know this distance here is 6. That's also 6. So that's going to be 6√2. Right, okay. So that means that the cylindrical coordinates are going to be 6√2 because you put the r first and then the theta and then the z. The z is still going to be 6. Okay, so let's try that. 6√2. Okay, do you want to do B together or do you want to do that on your own later?
I'd say together.
Together, okay. Okay, so here's the positive x-axis and here's the positive y-axis. And just looking at these 2 points, it's -6 and 6√3, so that's up 6√3. Okay, so what do you think? What do you think this side's going to be here now? This side over here. What do you think the radius is going to be?
Well, can't you just use the Pythagorean theorem to find that?
Yes, we can.
It'll be 6√3 squared plus 6 squared.
12, right?
Yeah.
Okay, but do you recognize the triangle? Do you recognize what this angle is right here?
Pi over 3.
Yes, that's pi over 3. So that means that this angle is 2 pi over 3. Okay, yeah, so that's pi over 3. It's a 1, 2, root 3 triangle. Okay, so that means this is 60 degrees, that's 30 degrees. Or pi over 3 and pi over 6. Okay, so there's your theta right there. And then your z is still going to be 5, so 12, 2 pi over 3, and 5. Should be the correct answer. Okay, great. So now we're ready to go on to the fun exercises. Rather than just reviewing things, we're doing new things. Yay. Okay, so the first one is to evaluate this integral, where E is enclosed by the paraboloid and the plane Z equals 16. Okay, so this paraboloid, what does that look like? Let's see, let me draw the...
Looks like a circle. Oh. Set.
It looks like a... Well, if you set the value of Z equal to some constant, like let's say you were to set it equal to 4, if Z were 4, then this would be a circle of radius 2, right? But if you were to set Z equal to 1, then this would be a circle of radius 1. Right? So if we were, so in other words, if we're here at 1, that's 1, then we basically have a circle of radius 1. That's what it would be. If we're at 4, then we would have a circle of radius 4, right? Okay, so it's going to come up like this. And come up like here. And come up on the back side. Okay, so you've got this thing right here. And then up here, it goes all the way up to, well, all the way up to 16. It's capped by this plane here at 16. But it's going to be a circle of radius 4 here, right, at this plane, right? Something like that. Well, I'm a little bit thirsty, so, but that would be nice to put some water inside and drink it. But then the problem is, if you set it down, it would probably tip over. So, oh well. So let's see here. So let's go ahead and set the integral up. This integral here. But how about we do this? Before we do that, let's look at the different players here. We have theta, R, and Z. Okay, and try to figure out where those are bounded, where each one of those is bounded. Okay, so let's see, we'll start with Z first, because remember the way that we want to do it is Z, you want to get that in terms of bounded by R and theta. By functions involving R and theta, I'm sorry. And then R, you want to get that bounded by functions involving just theta, or, you know, in this case, I don't think it's not going to be, it's just going to be constants actually in this case. But it's still, even if it's a constant function, it's still a function of theta in some default kind of way. Okay, so what are the bounds on Z now? Anybody want to take a guess?
Is it 0 to 16?
Yeah. When you're up here, it's 0 to 16, right? When you're up here, right here, it's 0 to 16. But if you're here, it's only from 0 to 4. No, I'm sorry, 0 to 2. Oh, wait a minute. Is it 16? No, no, no. No, no, no. It only goes, it's from 0 to 4 when you're up here. 0 to 4. It comes out, because right here it's a circle of radius 4, right? Here it's a circle of radius 2. So R is going to go from 0 to 2 here. I mean, or Z is going to from. Wait a minute. I don't know what I'm thinking. Okay, I started thinking about R. We're concentrating on Z here. Okay. So if you draw a vertical line that's inside here, a vertical line segment that's inside here. Okay. So Tika, you're absolutely correct. The top limit is 16, right? It's going to hit 16. Every vertical line segment inside here, it's going to hit 16 on the top. So that's a 16 right there. Okay. But now, what is the lower limit of what it hits? It's going to run into this, right? So that should be x squared plus y squared, right? So it goes from x squared plus y squared. So this is z equals x squared plus y squared. It goes from x squared plus y squared to 16. But we can't leave it as x squared plus y squared. We have to change it to cylindrical coordinates. And what is x squared plus y squared in cylindrical coordinates?
Oh, is it sine? No.
X gets changed to r sine theta, y gets changed to r cosine theta.
That was close.
And if you add those together, you're going to get r squared times the quantity x cosine squared plus sine squared, which is just going to be r squared. Okay.
That was close.
So that's why they ask you to do it in. That's why they ask you to do it in cylindrical coordinates, because this part right here becomes very easy, as opposed to having to deal with that, which might make it hard, or it's going to make it difficult, or maybe impossible to do the integration. Okay, and then what are the bounds on R? Dang. Okay, R is going to go from 0 to 4.
How do you get that?
Up here. Okay, so first of all, look at these vertical line segments, right? There's some of them that are up here, say, so right there, for example, there's one right there. Some of them that are really high here. Okay, but you're essentially, every one of these vertical line segments corresponds to a point up here in this disk up here that has radius 4. Okay, so that's going from 0 to 4. Okay, so you basically got these line segments coming down and intersecting the the bottom layer at some point, but it's all the action is up here. You can consider all the action up here. Okay, and then what's theta going to go from? Okay, the most typical thing you're getting on theta is from 0 to 2 pi. Okay, so this is 0, this angle here is 0, and as you come over here, this is pi over 2. This is pi back here, and then 3 pi over 2, and then back to 2 pi again here. So 0 to 2 pi, that's all the way around, which will give you the whole disk. Okay, so now that means the integral. Your theta is going to go from 0 to 2 pi. Your r is going to go from 0 to 4. Your z is going to go from r squared to 16. And then inside you have a z. And then your dv is going to be dzr, dr d theta. Okay, now because so I told you before there's a little trick that if you don't have no thetas here, 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 nothing, no thetas anywhere, then you can just take the difference here. So that's 2 pi minus 0, so that's 2 pi. Okay, so I showed you that trick before. Z, you're going to have to integrate that. What's that going to be? Z squared. Oh, wait, oops. Z squared r over 2. So the integral of z is z squared over 2, and that's going to go from z equals r squared to z equals 16. So you put a 16 in here. 16 in here are going to give you 16 squared is what? 128, wait. $256. Okay, so that's going to be 256 r over 2 minus, and then you put a r squared in here, so that's going to be r squared is r to the 4th times r, that's r to the 5th over 2 dr. Okay, then you integrate with respect to r. That's a 0, by the way. And here you have, well, 256 over 2, that's 128. You integrate this, you're going to get 64r squared because you have the over 2, right? And then this is going to give you r to the 6th over 12 from 0 to 4. Okay, put a 4 in, and that's 64 times 16 minus 4 to the 6th over 12. And that works out to be 4,096 pi over 3. Okay, great. Any questions on that one? Okay, let's do a couple more to get some better practice. Okay, so evaluate this integral where E is the solid that lies within the cylinder, above the plane z equals 0, and below the cone z squared equals 25x squared plus 25y squared. Okay, let's try to get a little picture of what's going on. Okay, so within the cylinder, x squared plus 9, s squared plus y squared equals 9. So if you were to change that to polar coordinates, you would get r squared equals 9 or r equals 3, right? Okay, what that means is that if you come out here to 3, and here to 3, and go around, then you go up like this, that's what this one's going to be. Okay, so you have a cylinder. It's centered, the center of the cylinder is the z-axis. Okay, now you have the plane z equals 0, so that's this right here going to be the lower bound of it. Okay, and then you have this cone here. Geez, what does this look like? So z squared equals 25. Okay, so this is going to be z squared equals 25r squared, which is z equals 5r. Okay, so that's z equals 5r. And that one is going to be, that's going to come up like this. Okay, so you have this cone here inside. Okay, so you have this cone inside the cylinder, and so the region is within the cylinder, above this plane, but below this cone. So your region is your solid is this right around here. I think that would be a better thing to put water in. That's not going to tip over. All right, but then you have too much solid there. Okay, so maybe that's not the best water container. Okay, but let's find out what the volume is of this. So next step is the limits of integration. So let's look at the limits of integration. Okay, z is the most difficult typically, and what's that going to be? So you draw a vertical line segment. I guess I should have drawn it to there. Okay, so you draw a vertical line segment. What's the bottom of the line segment going to be?
Is it going to be the plane of 0?
Yeah, yeah. So this plane here, the xy plane, is z equals 0.
Right.
Okay, and the upper limit intersects the cone, right?
Right. Is it going to be 5r?
Yes. So if you're intersecting some object, then you look at the equation for the object and you try to solve for this variable z. It's already solved for z. It's z equals 5r. That's going to be the upper limit. Okay, and now what is r going to go from?
0 to 3.
Yes, 0 to 3, because now you have a whole bunch of these vertical line segments, and you can represent every single one of them by going from r equals 0 to 3. Okay, so this is radius 3 right here. So all of them are represented by radius 3. Okay, and then theta?
0 to 2 pi.
Exactly, 0 to 2 pi. So usually it's going to be, typically it's 0 to 2 pi. Sometimes, you know, if they say stuff like, oh, it's going to be just the first octant, then that's a clue that it's not 0 to 2 pi. It's maybe 0 to pi over 2 or something. Okay, but we'll get to some of those later. Okay, so great. So now we can set the integral up. 0 to 2 pi, 0 to 3, and 0 to 5r. X squared becomes r squared cosine squared theta, okay, because that's x is r cosine theta, right? So you're going to square that. So that's what the, and then your dv is again dz r dr d theta. Okay. Okay, we can't use the trick because there's a theta right there. So boo. Okay, we have r cubed. And now there are no d's, there's no z's in here, right? There's just a dz. So when you integrate this, you're going to get z. So it's just going to be 5r minus 0. So that's just going to give us 5r. So the integration is going to give us 5r. Well, that's interesting. We have 5r to the 4th, right? That's r cubed, that's r. We have 5r to the 4th. What's the integral? It's just going to be r to the 5th from 0 to 3.
Wait, what happened to? Oh, okay, never mind. You split it up. Oh, okay.
Yeah, so I did a lot of steps. So like this and this gives you 5r to the 4th, and then when you integrate that, you're going to get r to the 5th, right? Okay. So you put a 3 in there, that's 243. Okay, so one of the things that you should probably take note of is the integral of cosine squared and the integral of sine squared, because those come up a lot here. But the integral of cosine squared is 1/2 theta plus 1/4 sine of 2 theta. That's going to go from 0 to 2 pi. Now, fortunately, when you put the 2 pi in here and the 0 in here, then that just is going to be 0. Okay, so that is just always going to be 0, right? And that means that when you put the 2 pi here, you're going to get 1/2 times 2 pi minus 0. Because when you put the 0 in here, you get 0. And so this is going to be 243 pi.
That's a lot of pies.
Oh yeah, that's a lot of pi. We could have a big festival with that, but it would probably be illegal right now. Or maybe we could call it a protest and go have, and we could probably, it probably wouldn't be illegal.
There you go.
Yeah, we just call it a protest.
But unless it's Ted, I don't want it unless it's Ted's. Well, I think they're closed.
Okay. Okay, so number 5. Oh wait, any questions on number 4? Okay, great. So let's go to number 5. Okay, so here it says evaluate the integral by changing to cylindrical coordinates. Okay, so as you can see right here, this would not be very fun to integrate this. The square root of x squared plus y squared. Wow. Well, actually, you would integrate the z first, but then you'd have this limit here. So this, imagine this times this and try to integrate it. That does not look very fun. Okay, so it's going to be a lot more fun if we do cylindrical coordinates. Okay, so what you have to try to do is figure out what's going on here. Now, one thing about cylindrical coordinates, if we do change the cylindrical coordinates, then let's try to figure out what the limits of integration would be. Okay, I get that's what it's all about, right? And z is already going from 0 to 16 minus x squared minus y squared. Okay, so z is already, the lower limit in z is already 0, right? What's the upper limit?
Would it be 4r? No.
16. So the upper limit.
For z, right?
What's that?
Why don't you just solve for z?
It's already solved for z. So the lower limit is z equals 0. So here, this is the lower limit. Here's the upper limit. Now I've taken the liberty of just factoring out a negative. Okay, so what is this in polar coordinates?
R squared.
Exactly. So the upper limit is just going to be 16 minus r squared. Okay, so when we do the integration, we're going to get that. Okay, what is this part right here?
It's just R.
Yes, that's just r. So that r just going to go right here. Okay, and then of course you're going to have dz r dr d theta. Okay, so now we're just going to figure out what r and theta are. So r, because that's that one. So let's see. Let's take a look at this right now. And what you can do for that one is just look at it over here. Okay, if that's x and that's y, right? So here, the lower, the limit's in y, right? It's in y. So we have y equals 0 to y equals the square root of 16 minus x squared. Okay, so y equals 0 is this right here, is the x-axis. What's y equals 16 minus, the square root of 16 minus x squared?
What are we solving for?
I'm just saying, what's this equation of right here? I guess you could square both sides, right? And get that, right? What's this equation of?
The circle.
A circle, right? But what's the difference between that and that? What's the difference between this equation of the circle and this equation? They look equivalent, but there's a big difference. Or maybe a small difference. Or there's a significant difference. What's that?
X can't be positive. No.
Yes. X or Y can't. No. X can be negative or positive, but Y has to be positive, right? So that's going to put us up here. So this right here is only the upper half of the circle. When the lower limit of integration is this, and the upper limit of integration is that. So really, we're just integrating over this upper half of the disk. Okay. So, what are the limits on R?
Ooh, I got it. 0 to pi.
That's theta. Theta is 0 to pi.
Oh.
Is
It
it
is
0
0 to
to
pi.
4?
Yes. R is from 0 to 4. So like you're going, so here's your R coming out like that. It goes from 0 to 4. Okay, from 0 to 4. So to get this part right here, R goes from 0 to 4, and theta goes from 0 to pi. And that'll do the trick right there. Okay, so 0 to 4, and then that goes from 0 to pi. And we're off. Yay. Okay, so let's see here. You're going to integrate in Z first. So essentially, oh, there's no, okay, so we can use that one trick where there's no thetas in there. So that's just going to pull a pi out right there. So all that turns into just a pi. Okay, and then we have 0 to 4. And then there's no z's here, so you're just going to get 16 minus r squared minus 0, which is just 16 minus r squared. And then here, these are r squared, right? So r squared times 16 minus r squared dr. That's 16r squared minus r to the 4th. Wow. R cubed over 3 minus r to the 5th over 5. Whoa. That's 16 times 4 cubed over 3 minus 4 to the 5th over 5. Okay, I stuck that into the calculator and I came up with 2048 over 15 pi. Final answer. Okay, so any questions about that? The key thing here is, first of all, just using these limits to get the limits on Z, right? And then after you do that, then these limits right here illustrate that you have this upper half circle, and then just use a polar coordinate strategy.